All right, welcome to the Explainer. Today, we're going to decode the secret language that engineers use to manage the electrical grid. You know, the one that powers our entire world?
We see bits and pieces of the power grid all the time, right? Those massive transmission towers on the highway, local distribution centers, and of course the outlets in our homes. All these things connect into this just gigantic, sprawling network.
So, that's the big question, isn't it? If you're an engineer, how in the world do you draw a map of something that enormous and complex? I mean, how do you get that onto a single page in a way that's actually useful?
Okay, so to really get why this is such a challenge, you need to know one key thing about our grid. It's what's called a three-phase system. Now, all that means is that it's a super efficient way to move power over really long distances. And that's absolutely crucial, because even a tiny bit of wasted energy, when you're talking about powering a whole country, well, that adds up to a ton of waste.
You can kind of think of it like three electrical signals all traveling together perfectly in sync. It's this beautiful three-part harmony, right? And it's key to how everything works. Gives us a nice, smooth, constant flow of power. But, and this is a big but, having three of everything is also where our main problem comes from.
So just imagine for a second, what happens when you actually try to draw all three of those phases for the entire grid? I'm talking every single generator, every transformer, every house, every factory.
Well, to put it simply, it's a nightmare. It just gets so complicated so fast. You end up with a diagram that's so dense and tangled, it's pretty much useless.
Yeah, take a look at this. This is what you get when you try to draw everything out for even a pretty simple system. It's just a web of lines, right? And think about it. If you misread just one connection in that mess, you could literally cause a blackout. The source material says it perfectly. A diagram like this is of little use as far as analysis is concerned. No kidding.
So obviously this wasn't going to work. Engineers needed a shortcut, a really brilliant, elegant way to just cut through all that chaos and see what's actually going on at a glance.
And that solution is something called a one-line diagram. Honestly, the best way to think about it is like a subway map. A subway map isn't a perfect two-scale drawing of a city, right? Of course not. It simplifies everything for one specific job, showing you how to get from point A to point B. Well, the one-line diagram does the exact same thing, but for electricity.
Wow, and this picture, this says it all, doesn't it? On the left, you've got that overwhelming, chaotic reality of the three-phase system. And on the right, the simple, elegant solution. It's clean, it's clear, and it's actually useful. It's the exact same system, just shown in a way smarter way.
But wait a second. How is that even possible? How can you just replace that complicated mess with one single line? I mean, why does that work? It really feels like you're just throwing away two-thirds of the information, right?
Well, the magic trick here is balance. The system is perfectly balanced. See, those three phases, they're basically identical copies of each other. They have the same voltage, the same current. The only difference is that they're just slightly shifted in time. It's kind of like three people jumping rope, where each person lands just a fraction of a second after the last one. It's predictable.
And this is the key insight. The source material puts it this way. Because the other phases are the same in magnitude and only have a phase difference, well, you don't actually need to draw them, because they're just predictable copies of the first one.
So what does that mean? It means engineers can do all of their calculations on just one single line, and then they can easily figure out what the other two are doing. It's an absolutely incredible simplification. And it's what makes managing a grid that spans an entire continent not just possible, but actually practical. How clever is that?
Okay, so now that we know why it works, let's learn how to actually read this thing. Like any good map, these diagrams have a key, a set of standard symbols. Think of it like a visual alphabet for the entire power grid.
Let's look at a few of the most common ones. First up, the circle. That's a generator, where the power is made. Then you've got this symbol that looks like two little coils. That's a transformer. It's what changes the voltage up or down. And that thick line, that's called a bus. Just think of it like a big main intersection where a bunch of different circuits all connect.
All right, so let's go back to our simplified diagram. Now, it's not just a bunch of random lines and squiggles anymore. Now that we have the key, we can actually read it. We know what it means.
So check it out. You can see the generator, labeled G1. That's creating the power. From there, the power flows through that first transformer, T1. Then it travels across the transmission line, goes through a second transformer, T2, and finally, it gets to the load. The load is just wherever the power is being used, like a city or a big factory. And just like that, you just read a power system diagram. Pretty cool, huh?
You know, the one-line diagram is such a great reminder that even inside the most complicated systems in our world, there's often this beautiful, elegant simplicity just hiding in plain sight. So the question is, now that you know this language, what other hidden maps are all around us, simplifying the crazy complex systems we rely on every single day? Thanks for joining this, Explainer.